Hi, I'm Scott Knockleby. In this video, we're going to look at the forward displacement solution for spatial manipulators. So by the end of this video, you should be able to solve forward displacement problems for spatial manipulators. So in previous videos, we looked at the Dennett-Hartenberg parameters, and we showed how we assign those for our links of our robot, and then we showed how those Dennett-Hartenberg parameters correspond to our homogeneous transform. All right, and now for the modified D&H parameters, our homogeneous transform is of this form, and we have the four Dennett-Hartenberg parameters. We have AI minus 1, we have alpha I minus 1, we have DI, and we have theta I. All right, so if you're using modified D&H, you need to use this formulation, all right, to get your link transformations. If you're using true D&H, all right, or sometimes called classical D&H parameters, which comprise AI, alpha I, theta I, and DI, you use this form for our homogeneous transform. So just make sure you're using the right homogeneous transform depending on which D&H parameters you use. Now, each row of our D&H table will generate one link transformation or one homogeneous transformation. All right, and we are going to use that in order to solve our forward displacement problem. So the forward displacement problem is, given the joint variables, what is the position and orientation of our end effector? Or in other words, what is the pose of our end effector? Okay, so the solution is we substitute the D&H parameters into the homogeneous transform equation shown on the previous slide. And we do that for each row of our D&H table, and we get a homogeneous transform for each link, and then we just have to multiply those all together to get the forward displacement solution. So if we want to find the forward displacement, it's simply the product of all those homogeneous transforms from I equals 1 to tool. All right, so it's just the product of each of these homogeneous transforms. So if we assume we say we had a 6-jointed robot, it would look like the following: T01, T12, T23, T34, T45, T56, and T6 tool. All right, so you multiply those all out, and we know we've done this right because our subscript matches our superscript. All right, and so on. I won't circle them all. So multiplying that out will give you the forward displacement solution. So T0 tool. If you were to do this, we'll get a rotation matrix that describes the orientation of our tool with respect to the base frame, and we'll get a position vector that describes the position of our tool with respect to the base frame. All right, and so this is our forward displacement for the spatial case. It would also work for the planar case. You could do the same thing, but this is the general form. So let's look at an example. We're going to use our 6-axis Rice industrial manipulator. All right, and just as a reminder, this has the layout of R, perpendicular R, parallel R for our main arm, then perpendicular R, perpendicular R, perpendicular R, where these last 3 joints intersect to form a spherical wrist. Okay, so again, this is our wrist. And this is our main arm. And as mentioned before, this is a very common layout for industrial robots. So we previously showed how we found the modified D&H parameters for this robot. All right. And so for each link, we have our 4 D&H parameters, and each one of these corresponds to a link transformation. So what we need to do is first substitute each row into our matrix here, into our formulation. So we're going to use this equation here. All right. And we're going to get a link transformation for each link. And if you were to do that, all right, I'm not going to write them all out, but basically substituting those D&H parameters into the homogeneous transform equation yields our link transformations. And so we're going to have 7 of them. All right. T0 describing frame 1 with respect to frame 0, 2 with respect to 1, and so on up to our tool frame. All right, so that's the first step. We find our homogeneous transforms. And then the next step is we need to multiply those all together. Okay, so you can do it all at once or you can do it piecemeal. So for example, we want to find T describing frame 2 with respect to frame 0. It'd be 1 with respect to 0 times 2 with respect to 1. You would get this. You then go to describe frame 3 with respect to frame 0. You would get this. And then if you see patterns like this, you can recall our trig substitution or trig identities we can use here, and we can substitute those in. And because joints 2 and 3 are parallel, that's why we can do this. And we get this more simplified version for description of frame 3 with respect to frame 0. We can do the same thing for the wrist joints, so joints 4, 5, and 6. All right, and this will be the transform describing frame 6 with respect to frame 3. And then lastly, we would multiply this all out in order to get our forward displacement solution. So we can make a note of that. All right, you would multiply this all out. To get the pose of our end effector with respect to our base frame. All right, we're not going to do that because it'll just be a fairly big mess, but you get the idea how it's done. So that is the complete forward displacement solution for our spatial 6 degree of freedom robot arm. And you would do the same thing for any other arm. Right? It all starts with the D&H parameters, and so that's why it's really important to get those D&H parameters correct, because that will then give you correct forward displacement. And as you'll see, we use our forward displacement to solve our inverse displacement. We use our forward displacement as well to develop our Jacobians. So it's a key to get those D&H parameters correct.